Hi, everybody. This is Mr. Fasoni, and today we're going to be going over Chapter 2, which is about quadratic functions. This is going to be the start of Chapter 2, and that section in Chapter 2 specifically is called Transformations of Quadratic Functions. So what we're going to be working with is very similar to what we worked with in Chapter 1.1 and 1.2, transformations of functions. The same three transformations still apply. We still have translations, stretches and shrinks, and reflections, which all apply the exact same way as they did with absolute value functions and other functions. The only difference here is that we're using quadratic functions, which are functions that have f of x equals some expression that has a maximum power of x squared. So x squared, or maybe x squared plus 3x minus 9, for instance. That would be considered a quadratic. I'm going to change my color here because that's not showing up very well. And all quadratic functions have the basic shape of what is called a parabola, which is just a U-shaped graph, very similar to the V-shaped graph, except that it's a little bit more, it's not pointy at the end, it's got a curve at the end. Let me see if I can make that a little bit nicer. So something like that. It's curved instead of pointy like a absolute value. So you can say this is a U-shaped graph versus a V-shaped graph for absolute values. All right, so let's continue forward. Our next thing that we're going to talk about is our goals for the section. There are two of them. First one is describing transformations of quadratic functions, and the second being writing transformations of quadratic functions. So really describing and writing are really the only two things that we're going to be doing in this section. So let's get right into the concepts. So our first concept is describing the transformations of quadratics. So we need the definition of a quadratic function first. So a quadratic function is a function that can be written in the form f of x equals a times x minus h in parentheses squared plus k, where a is not equal to 0. And the U-shaped graph of a quadratic function is called a parabola, which I already mentioned before. That's just the general shape of the graph. Typically, a quadratic equation points upward in its default state, but if we've got a negative a value, it will point downward. But regardless of how it points or how narrow it is, or if it's been moved, or maybe it's really wide, regardless of the shape, as far as the stretch or the translation or the reflection, they all retain that U in the overall shape. It's a nice curved shape. So our first concept here, translations of quadratics. So this is a basic chart from the book. It goes over how horizontal and vertical translations work. They work in exactly the same manner that we've seen in the previous sections, where either with horizontal stuff affecting the input directly, the x value directly, or when it comes to vertical translations, we are affecting the entire function with what we do. So in both these cases, our starting function is just x squared. That's the parent function of the quadratic function family. If we're doing a horizontal translation, that means we are modifying the input value x by some value h. We write this as x minus h. The reason we write it as x minus h because we want to account for that kind of backwards functionality of anything that we do with horizontal transformations. So just like mentioned before with the absolute values, if I've got a value on my x squared function, this black function here, if I want to move it to the right, which is in a positive direction, my h value is technically larger than 0, but I'm technically subtracting that h value. So to move to the right, I'm going to be subtracting h. If I'm going to move to the left, that means my h value is less than 0. Well, if I'm subtracting something that's negative, it becomes a positive. So if I'm moving to the left, I'm actually adding an h value. And that's described down here as well. It shifts left when h is less than 0. It shifts right when h is greater than 0. This works exactly the same way that we saw with the absolute value functions. And this actually applies to any functions that we're transforming. So when we get the hang of this, we'll be able to apply that to any types of functions we see in the future, whether they are logarithmic functions, exponential functions, square root functions, polynomials, etc. Vertical translations, as before, also work the same exact way. If I'm going to move the graph up and down by translating, I'm going to be adding a value to the entire function. In this case, my entire function is x squared. So I am modifying that entire function by adding a value k. And I should step back to the horizontal really quick. We modified that x value, so that means the entire parentheses is being squared. We're subtracting the h from x and squaring that whole thing. In this, on the right, we are adding a k value to the x squared, but we're taking that square before we add that k value. And like before with the absolute value functions, if I'm adding a k value, if I want to go up, I'm going to be adding k. And if I want to go down, I'm going to be subtracting k. And the rules are very straightforward with this. Vertical stuff does exactly what we want it to do. Shift it down if k is less than 0, so it's negative, and it shifts up if it's larger than 0 or positive. I should say greater than 0 or positive. All right, so our first goal then is to use that, what we know, to describe translations of quadratics. So we want to describe the transformation f of x equals x squared, represented by this new function, x plus 4 squared minus 1. Well, if I look at it, remember our standard format for these functions is a times x minus h squared plus k. That's our standard format. So I'm basically just looking for the values in this function. A value, we're not even really talking about the a value yet, but if there were an a value other than 1, it would be out here on the left of this x plus 4 squared minus 1. There's nothing to do there. Our next value is going to be our h value. I'm looking at this plus 4, but remember everything horizontal is backwards. So if I've got a plus 4 inside my parentheses with the x, that really means that I've got a negative 4. In other words, my function, I don't have an a value, so I'm just going to get rid of that. My function, if I started writing it, would really be x minus, and then I could put my h value in there, negative 4, close the outer parentheses, put that square value, and then I'd be at last adding my k value. Well, if I've got a negative 1 in the position of k, remember the vertical stuff works exactly like we would describe it. So if I've got a negative 1, it means it's moving down, which means my k value is also negative 1. So now I know what has happened with my function here. I've got an h value of negative 4 and a k value of positive or negative 1. And with those two values, I can describe what's happening. The h value means it's going to be a translation to the right by 4 units. The k value, that's my vertical translation. So it's a translation, and it's a -1, so it's going to be down by 1 unit. Those are my two transformations that are happening. And then if I wanted to graph this function, I'm actually just going to sketch it. But if I wanted to graph this function, well, I know that my original function is the quadratic function. It looks like this, a nice U shape. And you can think of the vertex originally being at 0, 0. So what's going to happen here, and in fact, I'm going to write that a little bit differently. The vertex is at 0, 0. It's right there. So what's happening is I'm translating 4 units to the right and 1 unit down. So my graph is just being moved. I'm going to change my color here. I shouldn't have used orange for this, since I used orange for my my k value. So let me redraw these axes. So if I'm going 4 units to the right, that means I'm going over 1, 2, 3, 4. That's 4 to the right, and then I'm translating down 1 unit. Down 1 unit. My new vertex is going to be right here at 4, -1. And if I drew my parabola, it would just look exactly the same otherwise, just moved. So every point on this graph has been moved to the right 4 and down 1. To the right 4 and down 1. Kind of goofed that up. To the right 4, down 1, etc. Fix that one. So every point on this graph, the red graph, has been translated to the right 4, translated 1 down, and it creates that new orange graph that represents our new function. That's all we're doing on this. Describe, and then if we want to graph, I'm going to ask people to sketch things. We'll do that more as we go through the chapter. Our goal by the end of the chapter is to be able to look at an equation and put together a basic sketch very, very quickly. It doesn't have to be perfectly accurate, but the major points will be represented. All right. Next concept here, we've also got reflections of quadratics. So this is continuing concept 1 of writing or describing the translation and graphing it. So we have reflections, and they work the exact same way they worked in the past. Again, if I have a reflection over the x-axis, remember, reflection in the x-axis or over the x-axis, that means I'm treating my x-axis like a mirror, which means everything that was above, say it's a happy face, gets reflected below. And same with anything below would get reflected above. I can't do this very well. Something like that. So if I'm reflecting over the x-axis, that means I'm putting a negative sign in front of my entire function. So in this case, my entire function is f of x, or x squared. So I'm putting that negative sign right out front. And it reflects the entire function. The black parabola gets reflected down and becomes a red parabola. Flips it over the x-axis. Reflections in the y-axis work the same way as they did on absolute value functions as well, but I'm affecting the input only. So the x is my input, x is my input. So that means I'm going to put a negative sign right in front of the x before I square it. And if I square a negative x, well, that just takes me right back to x squared, doesn't it? Negative times negative equals positive. X times x equals x squared. And in this case, the original function, which would be a black parabola, would be in the exact same location as the reflection over the y-axis. Because remember, the reflection over the y-axis means I'm reflecting it over that vertical axis, which means everything on the right side gets reflected to the left. I've got a happy face over here, it gets reflected over there. And that's it. And it even mentions at the bottom, y equals x squared is its own reflection in the y-axis. Last concept for part one are stretches and shrinks of quadratics. This is kind of the toughest one, but just be aware that it works the exact same way. If I'm stretching horizontally, that means I'm affecting the input directly. The x is my input, so if I'm stretching it or shrinking it horizontally, that means I'm multiplying it by some value a before I even square it. And remember, everything's weird and backwards with horizontal stretches and shrinks. So if I want to shrink it horizontally, which would be this blue graph here in the middle, everything's coming in from left to right, it's shrinking. That means my a value is going to be greater than 1. And that mentions it down here as well. The horizontal stretch, oops, I'm sorry. I talked about the shrink first. The horizontal shrink is when a is going to be greater than 1. A horizontal stretch, on the other hand, is when everything moves away from the x-axis to the left and right. It expands horizontally. So we end up with an a value that's between 0 and 1. So if I'm stretching it, it's doing the opposite. It's getting bigger horizontally, but the value that we're using is actually a very small value between 0 and 1. Same exact concept from before with absolute value functions. With vertical stretches and shrinks, it's a lot more straightforward. Again, I'm stretching the entire function. This time my entire function is x squared. So if I'm stretching or shrinking it, I'm multiplying the entire function by the a value. So I take x, I square it, then I multiply by a. If I do that, if my a is greater than 1, then it's going to be a vertical stretch, like in the blue picture. It's getting stretched vertically, which makes it look like a horizontal shrink, and the graph grows taller. If I'm shrinking it vertically, then I'm multiplying by a value between 0 and 1, a small value. And that causes the entire graph to get shorter, which makes it look wider. Kind of think about like those funhouse mirrors, if you've ever been to the fun houses in the fair. Some of the funhouse mirrors make you look like you're tall and stretched out, but it also makes you look like really, really skinny. Or if it's one that makes you look really short, it makes it look like everything gets wider. So you shrink down and get wider at the same time. It's the same idea there. So those are stretches and shrinks. So let's see this in action. We want to describe the transformation. We've got two transformations here. We're starting off with f of x equals x squared, and we want to describe the transformation represented by the function g in both situations. And then we want to graph the function. Well, I'm going to look at this, and remember, I'm looking at my a values for this. The standard form for these functions, again, is a times x minus h squared plus k. In this case, I don't have any k value. Actually, I take that back. I've got a k value on the second one. I don't have any h values though. So keep that in mind. We have no h values there in this function, but we can have them. But we're mainly looking at the a values to start. In this first one, I've got -1/2 times x squared. So that -1/2 is being applied to the entire function. So I can say that this is going to be a vertical multiplication of some sort. And since I have a value that's between 0 and 1, that means I've got a vertical shrink. But not only is it a shrink, I also have a negative sign. So I have an a value that's both a negative and a small value. So I have a negative sign, which means I also have a reflection. So if I wanted to describe the transformation, it would just be a vertical shrink by a factor of 1/2 and a vertical reflection. It's a mess. So I'm doing two things, a vertical shrink by a factor of 1/2, and then I'm also vertically reflecting the graph. If I were to sketch that or graph it, if I want to get really technical, if I were to graph that, there's entirely too much red on this, so let's go green. If I were to reflect it, or to graph that, it would be reflected. So my original graph would look something like this. The reflection would flip it, and the 1/2 would make it wider or shorter. So it would look something like that. That's a really bad drawing. Let's try that again. So it's been vertically reflected, so it's pointing down, and it is wider or shorter because it's been shrunk vertically by a factor of 1/2. All right, let's do the next one. G of x, this one's a little bit more complicated. I've got a 2 inside the parentheses, so I'm multiplying my input by a value of 2. So I know that that is going to be a horizontal shrink. And then I also have a +1 on the other end, which is going to be my k value, which is going to be a vertical translation. So if I were to describe this, I would just say that I am doing a horizontal shrink. But if I want to describe this horizontal shrink, did it mention it in the little thing up at the top? Let's see. It's not mentioned, but if it's a horizontal shrink, remember, we're always working with the reciprocal. So even though this value is a 2, we know it's going to be a horizontal shrink. So I'm going to take the reciprocal of 2. So it's going to be a horizontal shrink by the reciprocal of 2, which if I want to take the reciprocal of 2, I can always do that over here really quick. The reciprocal of 2 is just going to be turn the 2 into a fraction, and then the reciprocal is just a flipping of my fraction. So my denominator becomes my numerator, and my numerator becomes my denominator. The reciprocal of 2 is 1/2. The official definition of a reciprocal is that a reciprocal, two reciprocals can multiply to the value of 1. So if my number is 2, I'm multiplying it by my reciprocal. 2 times 1/2 gives me the value 1. My number is 3/5. Its reciprocal is 5/3. I multiply those, I get 15 over 15, which is 1. So reciprocal is just another way of talking about, you could call it a multiplicative inverse. You can call it the value that anything can be multiplied by to get 1, etc. So I've got a horizontal shrink by the reciprocal of 2. I can rewrite the reciprocal of 2 as 1/2 for my factor. And to get more accurate, by a factor of 1/2. That's my horizontal shrink. And then I've got a vertical translation. Well, I'm just going up by 1 because I'm adding 1. So vertical translate, up 1 unit. That's it. Now I've used too much blue. Let's go ahead and graph what this is going to look like. So here are my axes. Again, my original function is the quadratic function, which looks like this. I am horizontally shrinking it by a factor of 1/2 and then translating it up 1 unit. So what it ends up looking like at the end, so I'm up 1 unit, and then it's just a lot wider because it's been vertically. I'm messing up my stuff here. I apologize, guys. Let's go ahead and fix this. I am horizontally shrinking by a factor of 1/2, which means technically that if I'm horizontally shrinking, it's actually getting narrower horizontally, which is actually going to make it look like it's taller vertically. So horizontal shrink by a factor of 1/2 and a vertical translate 1 unit up builds my new picture of my quadratic. It's been moved up 1 and shrunk in. That gives me my new function g. All right, last concept. There's only a few more slides worth of information left if I recall correctly. Let's zoom out real quick. Yeah, it's only 3 more slides. So the next concept is writing transformations of quadratics. So the lowest point on a parabola, which opens up if we're on the lowest point of a parabola. So what we mean by that is if I've got a parabola that looks like this, it has a lowest point right down here. Or the highest point on a parabola that opens down. Opening down means the arrows are pointing down, and the highest point will be up there. Both of those are called the vertex. So those are the vertexes of my parabola. And let's make those arrows a different color so it stands out a little bit. Okay. And we've got something called vertex form, which is the form that we discussed prior to this, a times x minus h plus k, a times x minus h squared plus k, where a cannot be equal to 0. Because if a is equal to 0, it multiplies all this other stuff out, and it would create a value of 0 for all of this. And if that were the case, we wouldn't have a variable anymore. The variable would be zeroed out. We cannot have an a value equal to 0. And the nice thing about this vertex form is that the h value and the k value literally tell us where that vertex of the graph is at. It's built right into the equation. So I can look at any of these vertex forms and go, okay, I know my h value, I know my k value, that's where my vertex is. And then the a value lets me know if I've got a reflection and possibly also a vertical stretch or shrink, or maybe just a vertical stretch or shrink and no reflection. So either both or one or the other. So let's see what that looks like. So goal 2, writing transformations of quadratics. So let the graph of G be a vertical stretch by a factor of 2 and a reflection in the x-axis, followed by a translation 3 units down of the original graph, f of x equals x squared, the original parent function. So I want to write a rule for G, and I want to identify the vertex. All right, so let's try to figure this out. If I'm starting with f of x equals the absolute value of x, my goal is to rewrite it and turn it into something called G. Well, we've got 2 different things happening in that first phrase. We're doing a vertical stretch by a factor of 2 and a reflection in the x-axis. Well, remember, the a values indicate a reflection and or a vertical stretch or shrink. So that a value already handles both of these things. If I've got a vertical stretch, that means I'm multiplying by some value other than 1. In this case, it's 2. And if I'm reflecting, that means that the number that I'm multiplying by, that a value, is also going to be negative. So just by that first part, I know that my a value is going to be -2. And let me change my color again. My a value is going to be -2. So if I try to write this out, I know I'm going to have a -2 in front of my function, the absolute value of x. That's taking care of the first part. The next part that we're talking about is a translation. 3 units down, so I know it's vertical translation, so that's going to be my k value. Remember, k represents vertical translation. And remember, anything vertical works exactly like we want it to do. So if I'm translating 3 units down, that means that I am subtracting 3 from my function. And now I've done all the transformations. My a value handled the first 2 transformations, and my k value handled the last one. So I could rewrite this as a new function. We're going to call it g of x. And g of x is equal to -2. That's my reflection and my vertical stretch, times the absolute value of x. I don't do anything to that because I've got no horizontal changes, so that just stays the same. And then -3 for the translation 3 units down of the graph f of x equals x squared. That's my rule, or my equation form of the function. And then if I want to identify the vertex, all I need to do is go back and think about this format. A equals x minus h squared plus k. I'll write it over here again. Or f of x equals a times x minus, I'm doing absolute value. I did not mean to do absolute value. I'm still stuck in chapter 1, guys. If this were class, somebody probably would have caught me. Let me fix that really quick. My function was x squared, x squared, x squared. Rewind. Apologies. So my original function was f of x equals x squared. When I modified it by multiplying it by -2, it became -2x squared, and then I subtract 3 from it. So I rewrite the function as g of x equals -2 times x squared minus 3. That's my new rule. I apologize if I've been talking about absolute values. Did I do that anywhere else? Everybody makes mistakes, guys. It's part of life. It's part of learning. Even teachers who are thinking about math all the time. All right. So let's go ahead and fix this. I want to identify the vertex. So I know the standard format of this type of function is f of x equals a times x minus h squared plus k. And I know that my h value controls the horizontal position of my vertex, and the k value controls the vertical position of my vertex. Well, if I go to my equation, I don't have an h value in there with my x. If I don't have an h value, there's still an h value in there, it's just I haven't moved anything to the left or to the right. So my h value is the default value, which is just going to be 0. So I could rewrite the first part of this equation as a times x minus 0 squared. And I actually know my a value also, so let's rewrite that. My a value was -2 because I reflected it and I stretched it out by a factor of 2. And then finally, I need to write my plus k in. Well, I know my k value in this case is going to be -3. So I'm going to go ahead and put that in for my k. That's going to be the vertical part of my position of my vertex. And now I know both of those points. or both of those coordinates for my point. I know that my vertex is going to be right at the point 0, comma, -3. And I'm done. I've created both the rule for my function, g of x equals -2x squared minus 3, and the vertex is going to be 0, comma 3, because it didn't move to the left or right at all. The x value didn't change, and it moved down 3. All right, one more to go. This one's a little bit different. It's a more complex graph that we're modifying, but the same idea works. Let the graph of g be a translation 3 units to the right and 2 units up. So I've got 2 translations followed by a reflection in the y-axis. So the y-axis means it's reflecting over the vertical axis. So that's going to be a little bit different. But we can calculate this out too, no big deal, of the graph. And then my original graph in this case is f of x equals x squared minus 5x. Notice it's not the parent function. This is still a quadratic because the highest degree of the polynomial in this case is 2, x squared. Even though I've got an x in there, it's still fine. And I want to write a rule for g based off this original function. So I'm going to start my work. F of x equals x squared minus 5x. What I'm going to do is I'm going to translate it 3 units to the right and 2 units up. Well, if I translate 3 units to the right, that's my first thing. 3 units to the right is a horizontal translation. So that means my h value, in this case, is going to be 3. But if I'm going to the right's a positive direction for the horizontal axis. So actually, if I'm going to if my h value is 3, that means I'm actually going to be subtracting 3 from my inputs. So if I do that first step again, my equation becomes x, and I'm going to be subtracting 3 for my h value from each of my x's, minus 5 times x, and I'm going to fill in the h value. So x minus 3, I forgot the squared, minus 5 times x minus 3. That's my horizontal translation. I've got that done. 3 units to the right is done. But I also have to translate 2 units up. 2 units up is easy though. I just tack that on to the entire function. Right now my entire function is all of this. So I'm just going to add 2 units for my k value to the very end of the function. I'll get rid of this box because it's getting in the way. So now my function is x minus 3 squared minus 5 times x minus 3 plus 2. I'm almost done. The last thing I need to do is reflect it over the y-axis. But what I want to do before I do that is do some evaluating. This will make things easier in the long haul if I just go ahead and evaluate what I can. So if I take care of this, I've got x minus 3 squared minus 5 times x minus 3 plus 2. If I want to evaluate this, in fact, let me go ahead and see if I can take a screenshot of this and move it over to the blank space to the right. Let's see if I can do that. Looks like it's going to let me. All right. I'm going to go to the right here. I'm just going to paste this in here so I've got some work room. I don't know why I did that. Okay, so I've got this expression, x minus 3 squared minus 5 times x minus 3 plus 2. Let's just handle these from left to right. X minus 3 squared, well, that's just x minus 3 times x minus 3. Recall from Algebra 1 the FOIL method. FOIL stands for first, outer, inner, last, which means I'm multiplying my first values together, x times x, my outer values together, x times minus 3, my inner values together, negative 3 times x, and my last values together, negative 3 times negative 3. So what happens there is I get x times x is x squared, x times negative 3 is negative 3x, negative 3 times x is also negative 3x, and finally negative 3 times negative 3 gives me positive 9. I can combine like terms, so let's go ahead and do that. And I end up with x squared minus 6x plus 9. I've now simplified the first part. Let's continue. I'm going to deal with the second part now. 5 times x minus 3, well, that's easy. Minus, well, let's go up here. I'm going to get rid of FOIL. Minus 5 times x minus 3. This is just simple distribution. Negative 5 times x and negative 5 times negative 3, which gives me negative 5x. Negative times a negative becomes positive 15. And I'm just going to move these guys down because there's no other simplifying that needs to be done. And then finally, the last value we have is just a plus 2, which I'm just going to bring down. So this expression is a mess. Let's go ahead and clean it up. I've got x squares, which I've accounted for. I don't have any of those to combine. I've got some x's, negative 6x and negative 5x. So I bring down my x squared, negative 6x and negative 5x. Those combine to negative 11x. And then finally, 9 plus 15 plus 2 gives me plus 26. So now I've evaluated all of these changes that I've made, the two transformations that I've made, rather, the translations to the right by 3 and up by 2, and it's given me a rewritten form of this function, x squared minus 11x plus 26. Well, now all I have to do is that last transformation, which is a reflection over the y-axis. So I'm going to go ahead and do that. I'm taking my function x squared minus 11x plus 26. Let's erase this box. And I'm multiplying all my input values by a negative sign. So all my x's are going to be multiplied by a negative sign. So what that ends up giving me is negative x. I take whatever x is, I turn it negative before I square it, minus 11 times negative x, and then plus 26. Again, I evaluate. Negative x times negative x gives me x squared. Negative 11 times negative x, and let's go away from red. Let's redo this really quick. So negative x squared is just negative times negative, which is positive, x times x, which is x squared. Negative 11 times negative x, negative times negative is positive 11x. And then the 26 is unaffected because we only multiplied the input values by a negative. So I have plus 26. At that point, I have written the rule for G. Now I still haven't written the vertex though. But my vertex, we can find that relatively easily because I know I translated 3 units to the right and 2 units up before I reflected horizontally. Since I horizontally reflected, that means everything on the right went to the left, everything on the left went to the right. So I can sketch out what happened very quickly. I know that my vertex for a standard quadratic, my vertex is at 0, 0. Right there. Well, if I went to the right by 3, let's use pink. 1, 2, 3 to the right, and then I went 2 up. 1, 2 up. My new vertex would be right there. But remember, the last thing I did is I reflected over the y-axis, which means this point right here, this yellow point, which would be at 3, 2, it got moved from the right side over to the left. It got reflected over here somewhere. What's going to happen there is that my new vertex would be at -3, 2. The right side coordinate got moved to the left. The vertical coordinate doesn't get modified at all because it's being reflected only left to right. And my new quadratic would look something like that. Still pointed up, but with a vertex at -3, 2. All right. Well, that's it, everybody. I hope this was informative. Please try to get going on the homework. Please bring questions to class when we meet on Friday and Monday. For first and third, it's Friday. For fourth and sixth, it'll be Monday. Please bring your questions on either this or the homework. We'll see you soon. Thanks.